Okay. So let me scroll down to this part right here and put that back up on the board. Every lab has an objective. And the objective for this lab is to find the value for, let's see, for this equation. Silver plus 2 ammonias yields this complex ion. Silver 3 plus. We're looking for formation constant, which would be silver ammonia. There we go. We're looking for that value. But notice that this value, there's no chloride in there anywhere, right? So what we have to do is combine this reaction with another reaction. And let's see, here's what we're going to be using. These are our materials. We have 0.1 molar silver nitrate. We're going to have 1 molar ammonia. These are our reagents. We're going to have 0.1 molar potassium chloride. Actually, the concentration of ammonia is 1.0419, I believe, molar. So you'll need to use that value instead of the 1 molar when you do the calculations. And everybody knows how to use pipettes and burettes. So I need to go into that. We are going to use 125 milliliter Erlenmeyer flasks for our reaction vessels. Okay. So the reaction that we're going to couple with it is this one, just like we had on the board earlier. Okay. And we also know that the we know what the KSP for this one is. The KSP, actually, the KSP that we used in the slide set was one value. The one that we're going to use for this one is slightly different. The KSP for this one, we're going to use 1.7 times 10 to the minus 10, which is equal to solubility product of silver concentration, chloride concentration. There we go. So we're going to use that value. And that's on the second page. If we scroll down to the second page, you'll see it right here at the top. KSP is 1.7, 10 to the minus 10. And the accepted value for KF is 1.6 times 10 to the 7th. Right, so that's what you compare your answers to. Believe me, if you get 10 to the 7th, any coefficient times 10 to the 7th, you're doing good. Because this is a really tricky reaction. And I say that because it's hard to detect the endpoint. Okay, so in order to get something we can work with, we're going to combine these two equations here, and well, combine these two, and that will give us, let's see, that should be plus there. And combine these two, and we get, let's see, where's that for this? Yeah, I'll put it here. Combine this one with this one and get a third equation, because all of this is happening in the same solution. Plus 2 ammonia. Plus silver chloride solid. And now we have silver ions on this side, plus chloride ions, plus the complex ion. Okay. All right, as far as the math of this thing goes, we're going to take this expression right here and see if we can fit it into that one, because if we can put it into this one so that this equals something else that has chloride in it, then when we do our titration and we know the amount of chloride we added, it'll fit into that calculation. So let's see. What we're doing here is silver. We're attacking it from this place right here. So if we take this one and solve it for silver, then we get silver ion concentration at equilibrium equals KSP divided by chloride. Okay, does everybody see that? I just rearranged this equation. This one, that one. This one's equal to that one. And then I solve for this one, so that means chloride goes over here in the denominator. And that's what we have here. Okay, so we're going to substitute this in there. And that gives us an expression we can use that has chloride in it. Okay, and silver's got, let's see, KSP divided by chloride. Yeah, times ammonia. Where? Okay. Now, mathematically speaking, the denominator of the denominator, this is the denominator, but this is the denominator of the denominator, is the numerator. Right. So we can rearrange this equation to equal the complex ion times chloride concentration divided by ammonia squared times the KSP for silver chloride. So this is the one that's going to give us the calculation. What we have to do is find out what's this concentration at equilibrium, 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 and that's constant. Then we can calculate KF. So that's what we're after. Okay, so how do we get there? Well, we're going to titrate a solution, and what we want to do is determine how much chloride did we have to add to make this appear and stay there. That's the end point. So when we do that, it's difficult to see because silver chloride in solution, when you form it as a precipitate, is very small particle size. It's difficult to see, and they're kind of white, opalescent. So it would take, you'd have to go past the endpoint to see them in ambient light. So what we do is use the Tyndall effect. Remember that one? If you have a suspension, let's back up. If you have a solution and you shine a light through it, then you can see the light on this side with your eye. But if you're looking at it from this side, you don't see anything. You don't see the light beam in the solution. But if you have a suspension, which is our case, the precipitate forms in the suspension, then you can see the light beam in there. And that you can detect a lot easier with dim, room lights will be dim. You can see that light beam shining through there. And all you have to do is like move it up and down. You can see the light beam move. So we use the Tyndall effect to identify the endpoint more accurately. Okay. Now, as a practical matter, we've got this set of conditions where we take 5 milliliters of 0.1 molar silver nitrate, and we add so much of the 1.0419 molar ammonia, right? In the first one, we've got 5 milliliters. In the second one, we've got 10 milliliters. And we dilute all of that to 100 milliliters in a volumetric flask. Okay. I ran both of these yesterday.
How come this bottom's so grayed out? Are we just doing?
Yeah, it's too much for one lab.
Okay, so
Right. We could do them. I mean, if there's enough time left over, you're welcome to try them. Right. But I ran the first one, the second again, because I wanted to be sure the procedure with the reagents that I have currently, because I had to remake one of them. And I found that the volume of 0.1 molar potassium chloride that I needed to reach that precipitate was a little over 1 milliliter. And the burette only has divisions of tenths of a milliliter. Right? So you have to estimate between tenths. So there's really more room for error when you only have, when your volume's only moving that much. So I tried the second one, and I went between 3 and 4 milliliters. I think that one will be easier to work with. So let's just do the second one. Do the 5 milliliters plus the 10 milliliters of ammonia and dilute it to 100, and do that one in triplicate. Okay, so we do 3 of those titrations and then average the results. And if you got time, you're welcome to go to the higher concentrations of ammonia. As you increase the amount of ammonia, it takes more chloride to get that Q value up. So 15 would probably, I don't know, it might take 10 milliliters of KCl, and 20 might take 15 or 20 milliliters. So, but I think you can fill the burette up once, start at 0, and you can get less than 10 milliliters of your solution. One of the reasons you want to start at 0 is because the first one is just you read the burette, and that's your value. But the other reason is those burettes are funny. They're really finicky about the head pressure. Right? The taller column makes drop formation more reliable. Right? If you have more pressure, a higher column of titrant, then it's easier to control. Once you get down to the lower volumes, yeah. It's more difficult. Okay, so we're going to do 5 plus 10 to 100. Now, the concentrations, of course, of these reagents changes because we're diluting a known concentration to a known volume. But what's the final volume? That's the question. The final volume is 100 plus the volume of KCl you had to add. Right, so we have to take that into account because remember, equilibrium is all based upon concentrations. So that's where I'm going next with calculations. Once you've determined the volume of potassium chloride that was dispensed, then we need to go, we need to be able to set up an ice table using this expression right here. Okay, so what I've discovered and what the authors of this method obviously knew is that sometimes it's easier to determine outcomes on an absolute molar basis first. In other words, how many moles did you start with of each of these components? And then how many moles did you end up with at equilibrium? And once you know the number of moles of each component at equilibrium, then you just divide by the volume. And you get the concentration that you can insert into that expression. So that's why this next table is initial change equilibrium, but it's not in concentration, it's in millimoles. Okay, and this particular one is based upon the data that's above it right here. Right there. So what it says is that initially, before, with the amount of potassium chloride you added, we're saying, okay, I added this amount of chloride ion, but the reaction hasn't occurred yet. That's what initial means. So we've got 5 milliliters of 0.1 molar silver nitrate, and 5 times 0.1 is 0.5, like millimoles, because the volume is in milliliters. Okay. All right. So that's what you start with. And the ammonia you added in there was 5 milliliters of 1 molar for this problem, which would be 5 millimoles of ammonia was added. And you titrated it. The problem says you titrated into that 100 milliliters, you titrated 1 milliliter of 0.1 molar potassium chloride. So that means you have 0.1 millimoles of chloride to begin with. Okay. And let's see, use my pointer here. On this side, we're saying that before the reaction occurs, you've got no complex ion and no chloride on this side. So notice we've got chloride here and we've got chloride on that side. So you start here with 0.1 molar, but the reaction says that we consume all of the silver and we consume enough ammonia to be stoichiometric with the silver, which would be twice as much ammonia, right? So you're using 2 times the amount of ammonia as you do silver because of the ratio of silver to ammonia. Right here. So for every one of these, use 2 of those. That's why this value is, where is it? That's why this value is 0.5 here, and you're losing 1 millimole of ammonia, but you're losing all of the chloride because at that point we're at the equivalence point. Okay, so how much change of the diamine silver 1 complex ion do we have? Well, we have plus 0.5. Because for every 1 silver you lost, you show up here with another one. Right? And we're adding that chloride from the other side. So now at equilibrium, you have no silver ion. You have no free silver ions in solution at equilibrium. And you have left, let's see here. My cursor's not. Now you have 4 millimoles of ammonia left, and no chloride because the chloride's reacted. Right, so now the chloride's on the product side from here. And we have 0.5 millimole of, okay, so this is the equilibrium absolute amounts of everything in solution. Okay. So now you take those, oops, you take those absolute amounts and divide by the volume. So what was the final volume? Well, it was 100 milliliters to begin with, but you added 1 milliliter of potassium chloride, so it's 101 milliliters. So you divide those molar amounts, millimolar amounts, by the milliliters, and that gives you molarity, right? I proved that before, didn't I? Okay. So now we're calculating the equilibrium concentration of each of these values because, because that's the absolute molar amount divided by the the total volume. And now we get values for ammonia, complex ion, chloride, and we have the KSP. And now we can plug those into this equation right here. And when we do that, we get a value. And in this case, I got a value of 1.84 times 10 to the 7, right? Which is pretty close. What was it? Oh, it's not there. It's up here. Accepted value. There it is. 1.6 times 10 to the 7 is the accepted value. All right, so that's the one you would compare to your value when you get it. Right? And the reason I stuck this in there is so that you could almost cookbook it, putting the values in. And we're going to do 3 trials for the same reason we always do triplicates, at least. So you get 2 that agree to each other, and one of them that's just way off in left field, you can throw it out. It's called an outlier. Okay. So that's it. You just have to produce that value and show me your work. It's unfortunate that some students just, I don't know why, just generate a report with no calculations in it. So I don't know how you got the answer. This appendix, you don't have to worry about this appendix. What I've done in the appendix is just prove to myself and prove to posterity that when you put 1 molar ammonia in solution, that most of it is ammonia. Because ammonia will complex silver, but ammonium will not. So when you put ammonia in solution, you get some of it turned into ammonia, ammonium. Right, so I ran a calculation and determined that at 1 molar concentration, 99.6 of the ammonia is in that form, and the other 0.4% is ammonium. So I guess technically, once you determine the concentration of ammonia in solution, you could use this equilibrium procedure and determine what is the actual ammonia concentration in solution, and to put it in here and do the calculations for that value. And that would probably get you closer to the true value. I haven't done that yet because I'm lazy. But if I did, I probably ought to, just to see if it works. Otherwise, we assume the concentration is 1.041 millimeter. 99.6% of that would be like 1.03 something. But the concentration is not 1 molar. Ammonia is not 1 molar. Because we've diluted it by 100 milliliters, right? So, that brings up a good lesson for both of us. When you dilute, you get the same response here. The percent dissociation, let's see, as you decrease the concentration,
the percent dissociation should go up. Like when you dilute an acid, the percent dissociation goes up. So it may not, if we go from 1 molar to say 0.01 molar, how does that affect? It should decrease this concentration. No, I need to run that calculation. Right. So we don't have to do this lab until we get back after the 4th. So between now and then, I'm going to sit down and do the calculation and see how that dilution affects this actual concentration, and use the data that I got yesterday and recalculate and see if it improves my results. Yeah. And if it does, and I think it will, then I'll relay that to you guys somehow. Otherwise, you're free to go.
All right.